When you start.
Recording has begun.
Yeah, Zoom recording is remote. Yeah, let's first do that and then let's switch.
Maybe you can help me after.
Sure.
Let's just give 1 more minute.
So you need to do it on that link. Okay. Yeah, sure. Make it bigger. Thank you.
It's always complicated.
Yeah.
One at least the network works perfectly.
Yeah, that's good. They do.
Yeah, the other day I visited Georgia Tech. The idiom just doesn't work. It just doesn't work for me. I was like, oh.
Yeah. Go wrong doing it.
Yeah, as IT. We have enough time, so we will. The talk is supposed to at 11:30.
Okay, there's.
But 11:45 would be your next.
Okay,
so we have.
Hopefully it'll be interesting.
I think at least we have good attendance.
I talked about traffic in memory yesterday, so it's okay. Yeah, talk about something different. Not the same thing it was lately.
I'll just introduce. Hello, good morning. Welcome to ECE Colloquium. First of all, if you need to scan that, please do it. Because after that, I'm going to, we kind of enlarge that window and get this thing out of the place. All right. So anyway, today it is my great pleasure to have Professor Onur Mutlu visiting us. And Professor Mutlu is a professor at Computer Science, ETH Zurich. He's also a visiting professor at Stanford at this time. He was a faculty member, or still is, a faculty member at CMU. And previously, he held that Strecker early career professorship. His current research interests are in computer architecture systems, hardware security, and bioinformatics. He led his group for sure. So he and his students and his group has invented a variety of techniques that have significantly influenced the industry, and many of the ideas actually has seen the light in the commercial products. So very impressive works. And Professor Mutlu got his PhD and master's degree in ECE from UT Austin and BS from Michigan, and also BS with, actually in both computer engineering and psychology. So don't read my mind. Okay, so anyway, he started, Professor Mutlu has tons of achievement. He started the computer architecture group at Microsoft Research during his tenure there. And he had held different positions at Intel, AMD, VMware, and Google. He received many awards, including Intel Outstanding Researcher Award, HPCA Test of Time Award. I think that's about your work on run-ahead execution. I think many of students here know about that through the courses that we teach. So anyway, he also has, another IEEE Computer Science Society Edward McCluskey Technical Achievement Award, ECM SIGART, Maurice Wilkes Award, and many best paper or top picks paper recognitions at many systems, architecture, and security venues. So also another noteworthy activity, Professor Mutlu's computer architecture and the digital logic design courses and the materials are freely available through YouTube. And I think many of you actually benefited from that. So, okay, so without further ado, the floor is yours.
Okay, thank you very much, Leon, for the introduction. It's good to be here. I think I was here 8 years ago. Another 8 years to come back. So that I have an idea, how many people here are graduate students? Okay, most people. How many people are undergraduates? Some, okay, that's good. How many people are faculty? I see some of them from familiar faces. Okay, we'll get started. I think I'll get started with an error correction. I just realized that today is not January. Apparently I'm living in the past. How about that? And I think we need to be able to do that better in our computing systems also. This was not planned, by the way. Okay, so I'm going to talk about a specific area that we've been doing research on for about 12 years or so, which is the RowHammer problem. This specific area is very fascinating to me, and I think it's been a fascinating area of research and development in industry also, and it's going to get worse. So I will not leave you hanging with the answer over here. I don't think we're going to get rid of Bitflips anytime soon. But we need to figure out how to live with it and deal with it going into the future. When I talk about RowHammer, I usually show the picture of this bridge. This bridge looks beautiful, right? How many people know where this is? Okay, some people. Any guesses?
It collapsed.
Yeah, it collapsed, yes. It's a Tacoma Narrows bridge around the Seattle area. And this is what happened to it, a bitflip, basically. And I think bitflips are like this, really. You have some reliability issue and some bitflips, you get some corruption, and it becomes a security and safety problem also on your end. I call these robustness problems. And you can watch videos of this interesting thing over here. And I also show this picture. I talk about RowHammer to freshmen. I teach the freshman digital design and computer architecture class to, I guess it's going to be 600 students next year when I go back to ETH. And I give this picture and ask the question, like, these folks are actually happy right now constructing New York, but if this rod has a bitflip, they will not be happy almost immediately, right? So I think of security or robustness in general as preventing unforeseen consequences. I think it's a very general definition, and it could be criticized for being so general, but I think we're going to be in this regime. We really need to think about how to design our systems that can deal with unforeseen consequences. And we're not very good at that, frankly. I think going forward, we have big ambitions. We want to live in space. And space is a place where you may have a lot of unforeseen consequences. Even this world is a place where you may have unforeseen consequences. So I think we really need to change our mindset going that way. This is another thing that we're trying to build today, right? Mr. Bean invented this in 1990s, as you can see. And he has his own self-driving car. Again, he may not be happy if he starts getting bitflips over here. So what is RowHammer? Essentially, RowHammer is the fact that you get these bitflips in essentially all DRAM chips today. At the time we first tested this problem, more than 80% of the DRAM chips we tested were vulnerable. Today, it's all DRAM chips, so we're going to talk about a story of this problem. And it's really the first example of how a simple hardware failure mechanism can create a widespread system security and safety vulnerability. And people are writing articles that look like this. And I like this one because it says, forget software. Now hackers are exploiting physics. Increasingly, we're going to see things more like that as we actually interact with, as we make our circuits scale to smaller technology nodes, and as these circuits interact with environmental things that they may not normally be used to. Okay, so I'm going to give you a story, as I said, and we're going to take different approaches, but we've been working on memory for a while. This is a position paper that we were invited to write to the International Memory Workshop some number of years ago, as you can see. And we argued here that memory should not be designed alone. Memory should be designed with the system together. And if you really want to scale your system, as well as memory, you really need to take a systems approach to it. I'm going to give you examples of this. So today, we're designing memory and compute as compute. But going forward, I think we should merge them. I gave a talk at Duke University about memory-centric computing yesterday. It was all about processing in memory. And it's partly motivated by what I'm going to talk about today, which is we're having a lot of difficulties in scaling memory, so we need some intelligent computation mechanisms inside the memory, more and more. And hopefully I'm going to give you some examples from industry that this is really happening today to solve the RowHammer problem, but we need more and more. Does that sound good? Okay. Okay, so we're going to do a deeper dive. Basically, we're going to talk about memory that's used in all main memories today, essentially almost all computers. And this is DRAM, dynamic random access memory. DRAM stores charge in a capacitor. It's charge-based memory. Let's see if this works. Okay, maybe I'll not do it. It's too small. Basically, you store charge in this capacitor, and you need to access that charge to determine whether this is charged or discharged, which is essentially 1 bit. For this to work, both the storage device and the access device, all of the sensing circuitry should work. They need to be large enough for reliable sensing and large retention time, etc. And as you want to pack more data in main memory, you need to reduce the size of these structures. And as you reduce the size of these structures, they become smaller and more vulnerable to noise. There are many, many noise effects. We're going to talk about a special one. But before I go into that special one, I'm going to talk about one other noise effect, which is the retention time. And this is the more physical picture of this. It's, basically, it looks very different physically, right? This is the virtual picture. This is the physical picture internally when you actually implement these things. So we've been very interested in these noise issues and reliability problems. Some time ago, we did some study with Facebook. Over the course of 1.5 years, we studied all of the memory errors that they have in their production data centers all over the world. This is a lot of memory, a lot of servers. It's actually fascinating to see this. And they didn't allow us to publish how much memory there was, how many servers there was, because they were concerned about revealing the size of their fleet, which may affect their stock price, for example. But we were able to publish interesting data where we showed, I'm going to show you just one figure over here. This is the DRAM chip density that's employed in the server. It increases from left to right, as you can see. So denser chips are over here, which have more gigabits of data. And this is the server failure rate that you observe in the field. This is really in production data centers, servers. So you see that there's a strong correlation. Ignore the metric over here, that you need to do some important calculations to figure out how to figure out that metric. But the takeaway is that as DRAM chips get denser, servers fail more. That's a correlation study. Why? Because denser DRAM chips have smaller cells that are more vulnerable, and cells are closer to each other also, so they affect each other. Okay. So if you're interested in this analysis, you can take a look at this paper. There are other papers also in the field. So we wanted to understand things like this more. So we built a lot of FPGA-based infrastructures. I'm going to talk about our studies with this FPGA-based infrastructure quite a bit. Essentially, this is the first infrastructure that we built on the bottom over here. It was kind of a makeshift infrastructure, as you can see. But this FPGA, we can program the memory controller, and we can plug in different DRAM modules, and we can test the DRAM modules for different properties. What happens if I get rid of the refresh that happens in DRAM, for example? Which cells fail? When do they fail? Well, what does the retention time look like? Can I get rid of refresh in DRAM? Because that's one of the issues. In fact, that was the reason why we built this infrastructure, to understand the retention time problems in DRAM chips. Because that's one of the scaling problems. As you reduce the size of the DRAM cell, it stores less charge, and you need to refresh it more often. And we wanted to get rid of that refresh, but if you want to get rid of that refresh, you need to really understand the problem. So that's why we built this infrastructure, and this is the more scaled up version. We open sourced it in 2017, and people have used it for various purposes. And more recently, we open sourced a newer version that's a lot easier to program, and it works with DDR4 DRAM chips. If people are interested in doing studies like this, it actually works with many different FPGA prototypes. You just need to provide your own FPGA. Unfortunately, we don't supply that. We're in the academic budget. You can ask industry to provide the FPGAs, of course. And you have quite a bit of industry over here. They should be providing resources, right? But you can actually download the source code, and we'd be happy to help if you are interested in doing studies like this. So why did we build this infrastructure? As I said, we wanted to study data retention properties. It turns out because of manufacturing process variation, the retention properties of different cells in a DRAM chip are quite different from each other. And DRAM chips are designed so that you can refresh everything at the worst case retention time that's determined by the manufacturer. So you refresh everything every 64 milliseconds at the time. Today, that reduced to 32 milliseconds, and at high temperatures, you're at 16 milliseconds or so. So refresh rate is increasing, which means that my cell phone on my pocket right now is refreshing its memory and wasting power, right? But we wanted to understand the actual retention time by testing the chips, and this is what the retention time actually looks like. So if you look at this picture, you see that a very small fraction of the cells need to be refreshed very frequently. Most of the cells, you can reduce the refresh rate by about 4x. And this way you can actually get rid of a lot of refreshes. But if you really want to build this, you really need to understand your cells. And it turns out this is not an easy problem. I'm not going to talk about this a lot, but this is the reason why we built this infrastructure. It turns out the retention time is very much dependent on location, value pattern that you store in the cell, and because that determines the coupling between different cells, and also the time, which is interesting because there are some quantum-like random effects that change the retention time randomly. Anyway, we wanted to understand these things, and we wrote these papers that you can read. These are some initial papers. We wrote some other papers also later on. This is still an important problem. I think DRAM retention or data retention in DRAM and flash memory is important, but also other memories too. Okay, so while we were interested in this retention time studies, we were actually quite interested in other noise effects also. In fact, I'm going to show you another infrastructure. We had another FPGA-based infrastructure for testing flash memories. And in flash memories, you have very similar issues, retention, read disturbance. So we asked the question basically, can we see other effects in DRAM? And we were actually working with Intel quite a bit on this. And we essentially found out that that was the case. So we tested the read disturbance errors, right? So what is a disturbance error? Essentially, RowHammer is a disturbance error, meaning if you activate one row in DRAM, that activation causes disturbance in physically adjacent rows. So what is activating one row in DRAM? DRAM consists of rows of cells. It's a two-dimensional array, basically. When you want to access one location in one of the rows, you need to apply high voltage to that word line. This is called activate in DRAM. Now, if you want to access something else, some other row, you need to close this row, meaning apply low voltage to that word line, or this is called precharge in DRAM. And these are valid operations. So if you keep doing this repeatedly, activate, precharge, activate, precharge, activate, precharge, activate, precharge, and programs may do this relatively easily, it turns out in modern DRAM chips, in physically adjacent rows, some vulnerable cells flip, meaning they lose their charge, because every activation causes them to lose charge by a little amount. And if you do it enough times before the cells get refreshed, you would corrupt data. Clearly, this is bad. This should not be happening, because we're not even writing to memory, right? We're reading from memory. We're activating that row. We should not be changing anything, let alone some other rows that may not belong to this particular application. It may belong to the operating system. So this is clearly bad. We call this the hammer row. We call the rows that are affected the victim rows. And we showed at the time, this is around 2012, 2014, we showed at the time that more than 80% of the DRAM chips that we tested were actually vulnerable. And there are only 3 major DRAM manufacturers in the world. So essentially all DRAM chips, most DRAM chips were vulnerable. You can guess what's ABC also, yeah. I'm going to put names later on. Okay, so this is a scaling problem. So we tested chips that were manufactured in 2008, and we tested chips that are manufactured until 2014. We did not see this effect in older chips. We started seeing this effect in chips that are manufactured in 2010, and essentially all the chips that were manufactured between 2012 and 2013 had this error problem. Why it's a scaling problem? Because basically cells are getting smaller and they're becoming more and more vulnerable. Cells are getting closer to each other. Okay, I think I've already said a lot of this. DRAM cells are not electrically isolated from each other. So access to one cell essentially affects the value in nearby cells due to electrical interference between the cells and wires. It's also called cell-to-cell coupling or interference. I already said this, but when we activate one row, the adjacent rows get slightly activated as well. So there are many device-level effects that I'm not going to go into in this talk. That's actually a fascinating area. How do you actually understand what's going on in the device level? Why is this really happening? There are multiple effects over there, and there are papers written on this topic. We actually cover some of those papers in some of the retrospectives. That's an active area at the device level also. People don't completely understand exactly what's happening because our devices have become very small. I'm not going to talk about the device level effects. I'm going to abstract it away like this, basically. When you activate or apply high voltage to a row, an adjacent row gets slightly activated as well. And vulnerable cells in that slightly activated row lose a little bit of charge. And if you keep doing this hammering repeatedly, if it happens enough times before the cells get refreshed, charge in such cells get drained and you cannot read the data that you originally stored there. Now, clearly, this depends on the refresh interval, right? If you keep refreshing very, very frequently, hopefully you should not be able to do enough hammering to cause a bit flip. So one way of solving the problem is refreshing memory very, very frequently. But remember, we want to get rid of these refreshes. Right? So there are two scaling problems, retention and RowHammer, and these work against each other actually. So there's kind of nowhere to escape. But hopefully we'll try to escape. So this is kind of going into the, I'll basically question where are we going with the memory scaling. So it's getting much tougher, and we have nowhere to escape in my opinion. We need to find architectural solutions to the problem. Okay, so hopefully that's interesting. Okay, so there are higher level implications. Essentially, if you get a bit flip at this level, if it gets exposed to your algorithm or programming language, then a lot of things can happen. Now, this bit flip is happening in DRAM, and DRAM is directly accessible, directly observable in your data structures. That's why this is actually a much more widespread problem than if this bit flip was happening in flash memory or hard drives, for example. Yes?
If you hammer a row, can you have more than multiple victims on top or below?
Yeah, I'm going to talk about that a little bit. But yes, there could be other rows that are affected also. In this paper, in this original paper that I'm going to talk a little bit more about, we showed that at least 3 rows are affected. DRAM manufacturers did some work to reduce that effect, I believe. But I'm going to talk about some more recent developments that Google did in 2022, where they showed actually that effect is still there. It's called blast radius these days. Basically, you blast one row and the radius can be large, right? Yeah. Okay, so basically, if you have a bit flip like this, you can actually induce this bit flip from a real program. This is a user level program that we wrote and open sourced. Later, works actually built on this program. It's very simple. It's it determines addresses X and Y that belong to the same bank. It basically bypasses the caches in the CPU. It bypasses the row buffer in DRAM, which is essentially a cache on the DRAM side. You can keep it that way if you don't know a lot about DRAM. And it basically ping-pongs activates to X and Y over here. And if the chip is vulnerable, hopefully you'll get bit flips. Now, in the paper, we also observed that if you sandwich one row between X and Y, you get a lot more bit flips. This is called double-sided RowHammer. And that's the way of getting the most bit flips today, essentially. Okay, so we showed that in real CPUs, you can actually induce bit flips. Don't get hung up on the values over here because it requires some work to actually get these bit flips. But today, every CPU is vulnerable, assuming you don't have a solution to this problem. Right? So it's a real robustness issue in the end. So when we actually wrote the paper, this is the first sentence from our paper, we said memory isolation is a property of is a key property of a reliable and secure computing system. And access to one memory address should not have unintended side effects on data stored in other addresses. I still believe that we should maintain this. And we said in the paper that someone can take what we did, our observations, and write a program that can hijack your computer or that can crash your system. Right? We did not go that route, but the good folks at Google Project Zero read our paper. They essentially replicated the problem, and they showed essentially this. I would recommend looking at their Black Hat presentation. This is Mark Seaborn and Thomas DeLien. This is actually a copy and paste from their blog post, some parts of their blog post. They basically read the paper, replicated the problem on their system. They developed 2 types of attacks. One takes over the Google native client. We're going to get back to that at the very end of the talk in a different way, in a historical way. That's not as interesting to me. But the other one's very, very interesting, which is they built a user-level program that would induce these bit flips and take over the Linux kernel. Essentially, you could become root in the Linux kernel. And the way they did it is they introduced a page spraying attack, which I'm not going to go into detail, but they were able to induce bit flips in the page table entries of this user-level program. And these page table entries point to the page table of the program. Essentially, if you're able to flip the right bits in your page table entry that points to your own page table, you can get write access to your own page table. And if you get write access to your own page table, you can modify your page table so that you can access anything in that particular machine. Right? So that's the core of the attack. I think of this as flipping the right enable bit of a page table entry that points to your own page table. Right? Of course, flipping the right enable bit is difficult, so they actually came up with a more, let's say, creative attack of doing this, but I'll leave the suspense for you to read their blog post. Many papers after this actually built on this attack if they wanted to take over the system. Okay, so people, this became more famous as the RowHammer vulnerability, and people start drawing pictures like this. They're actually very interesting pictures on the web. I have some of them in this presentation. So a famous hacker on the internet said, RowHammer is like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you were after. So if you're actually stuck in this room, and the doors are locked, don't worry. Keep banging on the wall and magically one door may open, if RowHammer is in effect. I don't know if it's true. Okay, so people started building a lot of interesting attacks on top of this. I'll go through a survey of this relatively quickly, because they're actually quite creative attacks. These folks from TU Graz, for example, showed that they could induce RowHammer Bitflips in a remote computer and take over that computer through JavaScript. These folks from TU Amsterdam showed that they could write a program that someone can download on their Android system, and they could figure out which parts of the memory are vulnerable to RowHammer, and this program over time essentially launches an attack to take over your system completely. And they exploit some interesting things in the memory allocation patterns of the Android kernel at the time. People accelerate this with GPUs. I think there's more work to be done over here. People actually were able to show that you could do this through the remote direct memory access engine across the network, essentially. These folks showed the same thing. You can see some interesting pictures. These folks show that actually, even if you may not be able to take over a system for whatever reason, you can leak private data. So you can actually use these RowHammer Bitflips to read data that you're not supposed to read. So this is a confidentiality issue as opposed to an integrity issue, right, earlier. More recently, there have been papers that show that if you actually induce these RowHammer Bitflips in the weights of a neural network, you can actually cause that neural network to be terribly inaccurate, basically. Otherwise, it could be accurate, but you induce these Bitflips and it becomes inaccurate. Now, clearly, if this neural network is used for a safety-critical purpose, you may not want to use it anymore, right? I'm going to talk about this later on, but industry has also been developing attacks, especially Microsoft and Google has been quite active in this area, and they've been developing interesting attacks. I will get back to this later on. So they show a different way of hammering in memory. So this may be another attack that you come up with. It's an easier attack than RowHammer, guaranteed, but maybe not the best attack. This could be a solution also, but I'm not suggesting that's a good solution. Okay, so we've written a lot of papers. I'm not going to go over everything over here, but I will do a deep dive. This is the most recent survey, but it doesn't cover what has happened in 2023 and 2024. So there's still a lot happening. Yes? Yeah.
How much ECC is going to help?
We're going to talk about that. So you have the same question? Okay, maybe I should answer it. Depends on the ECC. If you want to pay a lot and make it stronger, it can help. So we see at least, in many cases, we see 8 errors per ECC word. So if you want to have a really strong ECC, it can be helpful, but if it's not, if you have a weak ECC like today, yeah, maybe not. And people have shown that actually, even if you have ECC, you can exploit RowHammer as a security problem. This is also work from VU Amsterdam. They called ECC ploit. Okay, we're going to talk about solutions, and ECC is going to be one of them that I'm going to. I don't want to say dismiss. It could be part of a bigger solution, but by itself, it's a very expensive solution. Okay, so any other questions? And keep asking, keep interrupting me, so that's good. So I'm going to talk a little bit about understanding RowHammer, because understanding is necessary for building solutions, I believe. So we did a lot of work in our original paper to understand things. So our FPGA and service structure has been useful in both discovering it and understanding. So we tested more than 120 modules at the time. There are a lot of results in the paper. I'm going to highlight 3 of them. One is, what is the distance between the aggressor row and the victim row? Distance from a memory controller perspective. Meaning memory controller issues a row address, which rows from the perspective of the memory controller get bitflips. Now you would expect this distance to be 1, right? But this distance actually is not just 1, because there's some apart from the blast radius effects, there's some scrambling there's some address remapping that goes on in the DRAM chip for various reasons, especially reliability. That changes the essentially that you have a logical row address mapping in the memory controller that's different from the physical row address mapping in the DRAM chip. So there's an intermediate address mapping, and this is important to know, because if you want to develop a solution on the memory controller, you may not know which rows are impacted, right? In the DRAM chip, you know, hopefully, because you know exactly what's going on. But in the memory controller side, you may not know. So this is going to limit us on the memory controller side. Or at least your solutions on the memory controller side may be imperfect because of this. Okay, the other thing we looked at is, what if you change the access interval? Meaning, don't activate things as frequently as allowed by DRAM, standard today, but reduce the frequency of access. Of course, this will impact your performance, and if you want to get rid of every single bit flip, these are real results from real DRAM chips. If you want to get rid of every single bit flip, you need to activate very, very infrequently, like every 500 nanoseconds. So your DRAM becomes very slow at that point. So this is not a good solution. But if you do it selectively, you can throttle the accesses and you can get rid of some of these bit flips. So selective throttling is going to be a potential solution, as we will discuss. And then there's the other level, which is refresh interval. So this is, again, data from the worst DRAM chip from each manufacturer. This is at the time. All of these data has become worse, meaning RowHammer has become worse, as we will see soon. Essentially, if you reduce the refresh, if you increase the refresh rate or reduce the refresh interval, you'll reduce the errors, as you can see. And if you want to get rid of every single error that we saw, you need to increase your refresh rate by 7x. That's essentially what we don't want to do, right? Okay, because that's bad for performance, energy, etc. So I'll also mention the data pattern. So data pattern affects the coupling between the different cells. If you actually have a solid data pattern, you have some coupling. If you have different types of, different amounts of charge in adjacent cells, you have different type of coupling. And you get an order of magnitude more errors if the coupling is a lot worse. And later works actually exploit this also. Okay, there are a bunch of other observations in our paper that I'm not going to talk a lot about. So this is very different from retention cell. So there's not much overlap between cells that suffer from retention versus RowHammer, because this is a completely different failure mechanism, essentially. Errors are repeatable. This makes it a security problem. So if you can induce errors in one cell, you can induce an error again, again, again. So you can profile your DRAM, figure out which cells are actually vulnerable, and you can use that profile later on. ECC, we've already talked about. 4 errors became more later on. And we talked about double-sided hammering also. Okay, there's more in the paper that I'm not going to talk about. But what I'm going to talk about a little bit later is it's getting much worse. So I'm going to talk about some of these more recent studies. There are many dimensions to it that we haven't originally examined, like temperature, aggressor row active time, etc. Word line voltage is an effector. I briefly mentioned that. And actually, HBM chips, essentially all DRAM chips are vulnerable to this. HBM is clearly used a lot in our machine learning infrastructure today for both training as well as inference. And we see very similar issues in HBM and some other interesting issues because of the 3D stacking that happens in HBM. I'm not going to talk about HBM that much, but essentially all our infrastructure is vulnerable, I believe. Okay, now I'm going to talk a little bit about solutions, and then I'm going to switch between understanding and solutions during this talk. But feel free to ask questions. So how do you solve this problem? People talk about ECC, we talked about refresh, but when we discover an issue like this, there are chips that are vulnerable in the field. So you need to have an immediate solution, right? You need to protect them. And given the way we design our systems today, you have very limited possibilities. Essentially, the limited possibility is dependent on what can you update in your memory controller, because there's no updatability, let's say, in the DRAM chip itself. And there's very little you can do in your memory controller today, which is increasing the refresh rate. And that's essentially what everyone did. I'm going to mention that. But longer term, we probably should be thinking more carefully, because these issues are not going to get better. So I'm going to talk about the long-term solutions. So this is the solution approaches overall. Clearly, if you can solve the problem at the technology or device level by building more robust DRAM chips, that would be good. We don't know how to do this at low cost at this point. And DRAM manufacturers are actually good at trying to do this as much as possible. They're experts at the device level. They're experts at how the DRAM structure can be optimized. And they tried hard to reduce the impact of this problem. And even then, it's getting worse, basically. Error correcting codes. I think error correcting codes, I have a fundamental issue with error correcting codes in general for this particular, to solve this particular problem. So this is a problem where you know the cause of the error really well, right? Error correcting codes are very good at errors where you don't know the cause of the error well. It's random, for example. So for soft errors, error correcting codes is a great idea. But here, if you want to protect all of your memory with error correcting code just for this purpose, it may be a very expensive solution. But that doesn't mean that this is a bad idea. I think as you increase the strength of your error correcting codes, you get more robust memory, and you can catch some of these errors early, but although you may not be able to prevent everything if you don't have a strong enough error correcting code. Yes?
Could better materials help to
Yeah.
mitigate this?
So that's why I kind of said, put into the robust DRAM chips. Basically, better materials can help build more robust DRAM chips, but they can come at a cost. Essentially, we don't know how to have better materials at low cost yet. Yeah. So there are system-level solutions, like you can isolate the victim rows from aggressor rows by wasting a lot of memory, like separate all of the rows by 3 rows, for example. Now you're wasting a lot of memory capacity, right? And people have looked at this. This is tough, and also it's guaranteeing security is tough over here. So there are really 2 major solutions, in my opinion, that we're left with at this point. But maybe people are creative. Maybe you'll find some solutions. Who knows? One is reactive refresh, and reactive refresh means figure out which rows are being hammered a lot, either through probabilistic approaches or deterministic approaches, like counting how many times each row is activated, and refreshing victim rows, potential victim rows. This is good if you know which rows are victim, and which rows are adjacent to each other. So inside the DRAM chip, it could be possible. It's a bit harder outside the DRAM chip. And then proactive throttling says, again, figure out which rows are activated a lot, and before they cause bit flips, stop accessing them, right? And figure out what is a safe amount of time you don't access those rows. So these 2 solutions are actually can be made secure. Now the problem is all of this. Essentially, you need to add counters, for example. You need to have essentially complexity, cost. They have a performance impact. And we're right now at the space where we're trying to figure out how to navigate this complex space, essentially. You can add security as another potential trade-off metric, but I'm going to avoid that. I think we want to get rid of every single bit flip, because 1 bit flip can actually be essentially deadly, right? Okay. So what did the industry do? Essentially, industry initially increased their refresh rates. And this is Apple's security patch, and I like Apple because they reference work properly, let's say, both Google and our work. And essentially, everybody did the same thing, even though they were not, let's say, as concise and nice as Apple in their. So they didn't say how much they increased the memory refresh rates. I believe it's 2x, but that doesn't get rid of. That reduces the vulnerability, but that doesn't get rid of every single error rate. Okay, so our solution, which I believe can be made to be a part of a bigger solution, but it doesn't work alone right now, especially because RowHammer has become much worse, most probabilistic. This is very low cost. The key idea is very simple. After closing a row, the memory controller probabilistically, with a very low probability, activates 1 or both of the adjacent rows. And if you want to take into account blast radius, you activate more. And this probability can be determined based on how many times you need to access each row or activate each row to cause a bit flip, right? So we showed that you can get a very good reliability at the RowHammer thresholds we tested at the time. And if you're paranoid, you can change the probability value to a higher value. So this is actually interesting because it's very low cost, it's stateless, it's the lowest cost solution to RowHammer that I know of at this point. And so let me give you some numbers. At the time when we tested these DRAM chips, we saw that you needed to activate 1 row or hammer 1 row 139,000 times. That was the lowest value. That number has dropped a lot. So if that number is that high, this is a good solution in terms of overhead. But as that number goes down, this actually has higher overhead. Now, this could be implemented in the DRAM chip and memory controller, and it has been done both. So this solution has been employed partially in different parts of the system. Intel actually had a memory controller that implemented something like this. It was not exactly how we envisioned. But essentially in the BIOS, you can pick your RowHammer solution. It's either 2x refresh or hardware RowHammer protection. Now, if you click on hardware RowHammer protection, you can pick your probability. Now, I don't think this should be exposed to the user that much, so it should be done automatically, but at least it's a step in the right direction. It's a slightly intelligent memory controller, right? And you can configure it. Now, if you're paranoid, you can activate adjacent rows every other activation. But that's probably not a good idea. Okay. So essentially, this is different from increasing the refresh rate across the board, right? Increasing the refresh rate across the board activates all of the rows in DRAM more frequently. Here, we're selective, right? But if you actually activate adjacent rows after every activation, that's a lot of refreshes that you induce. Okay, so I think this sort of memory control is actually what we envision. You want this, some intelligence in the memory controller to enable solutions to this problem. And we're going to make the memory controllers more and more complex, as we will see. Yes, in the back.
Do you know what the adjacent row is?
So if you're in the DRAM chip, yes. if you're the DRAM manufacturer who is implementing the solution to the DRAM chip, you should know all of the address mapping.
No, that wasn't the question. I mean, you have to know the adjacent row that's being hammered, adjacent to the one that's being hammered, right?
Yes. So which rows are physically adjacent, right?
Right, but which row is being hammered?
So you know exactly which row is being hammered because that is the activation. You send an activation command to DRAM. Yeah.
So you have a counter.
Yeah, you can have a count for not for para, not for probabilistic row activation. So in probabilistic row activation, you basically flip a coin. If that probability is higher than that zero, if the coin gives you a number that's higher than that probability, you activate physically adjacent rows. Right? So this doesn't have any access counters. Access counter is another solution, counting the number of accesses to each row. And before you cross a threshold, you activate, you refresh physically adjacent rows.
Frequency.
Yeah. So this is a more probabilistic sampling-based approach as opposed to deterministic counter-based approach. Yeah, there was another question over here. Yes.
Yeah, I was thinking whether you activate nearby row, will you like increase the number of row you are hammering? For example, you were originally hammering just one row, but if you just refreshed all the adjacent row, you are actually hammering 3 rows. But I realized that probability will because it's relatively.
That's right. They're relatively small, right? Yeah.
I see.
Yeah. But we're going to talk about that. That's actually a real concern. The solution that you propose is actually activating rows if you do refresh-based solutions. And that could actually cause Bitflips also, as we will see soon. Well, maybe not so soon. Yeah. Yes, please.
You mentioned that having denser memory sticks affected, had higher probability of having RowHammer.
That's correct.
If you take a look at what gas latency or enabling XMP on the same memory stick has an impact on these type of attacks?
Yeah, I mean, if you reduce the latency, not the CAS latency, but here the row activation latency, the latency between 2 row activations, you will be able to hammer more.
No, I mean, if you take 2 different memory chips and come of different gas latency, does the chip with the lower gas latency have lower chance of RowHammer attacks?
So CAS latency is column access latency, right?
Yes.
In this case, it doesn't matter that much because what we're trying to do is reduce the latency between activates. So that's really the RAS latency plus some other things, pre-charge latency. So it's really TRAS plus TRP, pre-charge, that we're dealing with.
Kind of has no effect.
Yeah, CAS doesn't have that much effect, no. But TRC definitely has a big effect.
What about XMP, maybe overclocking the memory? What's the impact on that?
Yeah, I mean, overclocking, it depends on if it affects latencies. If it doesn't affect latency, overclocking normally affects the bandwidth, right? That needs to be studied more. Meaning, it'd be good to see if there's some effect of the outside frequency. Probably not as much because it's an internal effect of the array and it's relatively isolated within the array. Yeah. Okay, so basically I'm going to argue for intelligent memory controllers. And we know how to build intelligent memory controllers except we know how to build it for other memories, like storage. So this is our infrastructure where we actually did a lot of studies on flash memory. And flash memory has a very sophisticated control because if you look at flash memory actually saw these scaling problems earlier than DRAM. And in fact, if you manufacture flash memory, most of the bits don't work because there's a lot of noise in there, right? What makes it work is the controller. The controller does a lot of voltage optimization, reference voltage optimization, and also read disturb detection, refresh, ECC, etc., and they make the bits work. So we wrote a lot of papers on this topic also, but this is a summary paper of what we have done over maybe 8 years or so. It's fascinating. So basically, we need to build similar controllers for DRAM, except DRAM is difficult because DRAM is much lower latency than flash. So if you add a complex controller before DRAM, you're wasting the speed of DRAM, right? And we don't want to waste that speed. Okay, so I think going forward, I'm going to talk about history also, but we need to understand more. And I'm going to give you some examples. Basically, many effects still need to be rigorously examined, right? Aging, for example, worries me. We have a paper coming up at HPCA that shows that if you actually keep hammering for 68 days, some of your RowHammer thresholds go down significantly. Meaning, if you tested your DRAM chips before they were used in the field and determined their RowHammer threshold and said, oh, I'm going to refresh the rows every n activations, for example, to that row, that n becomes lower in the field. So that's not good, right? So how am I going to trust the DRAM if it's deployed for 5 years, for example. Environmental conditions, I'm going to talk about some of these. Memory access patterns and memory control and system design decisions. These all affect the bit flips that you get in the end. And then we also need to think about how to solve the problem, because I don't think we have a complete solution yet. I'm going to talk about both industry and academia later on. We need flexible and efficient solutions, I believe. Patchability, reconfigurability, and programmability will be important. And I think we really need to solve the problem across the stack. Because you may actually translate this, even if you solve the problem perfectly, this may be translated into a performance problem or denial of service problem. We may discuss that. Now let me give you some of what happened in 2020 and 2023. I'm not going to talk a lot about what has happened in the security community, which is fascinating. There's a lot, but talk about more understanding and solution perspective. Yes?
So coming back to, I think you talked about Flash.
Yeah.
Intel, at least for a certain period of time, they funded the 3D crosspoint
Yeah.
for a while, and then I guess they abandoned it because it didn't meet their cost and requirements, and speed requirements.
Yeah.
If it had succeeded, would that have been a better solution? Because it would completely get rid of DRAM.
Yeah.
And directly access.
I mean, that's a very broad question, but the answer is no. Because I'm going to actually mention other memories later on. So all of the memory technologies are going to have problems like this. Flash is having it. Other emerging memory technologies have other problems also that require intelligent controllers, actually. And Intel had a relatively intelligent controller to deal with issues of phase change memory. But basically, we have nowhere to escape, in my opinion. We don't know how to build memories that are not vulnerable at scale. Right. Of course, you can build a memory that's not dense enough, and then you get rid of some of these problems, but that's not going to help with improving performance. Okay, so while we were doing these studies, we actually wanted to also understand what has happened to RowHammer. So this is a study that we published in ISCA 2020, and there's a reason for this, actually. So what happened in industry is fascinating. Industry, basically, Intel was building these memory controllers, and at some point, DRAM manufacturers said, we solved the problem. And everybody believed that. So, because everybody wants to get rid of the problem, right? DRAM manufacturers said, our DRAM chips are not vulnerable, because we have some mechanisms internal. They didn't say what mechanisms those are. They didn't say anything, essentially. And in fact, Intel stopped having their memory controllers like that. So they didn't develop that direction because of this, partially. And we questioned this, of course. And we did several works that questioned this. I'm going to talk about some of them first. I'm going to talk about the understanding part first. So we wanted to understand where the technology is going. So we actually did a more larger scale study. We tested 1,500 chips from many different generations plus different technologies. And we found out that newer DRAM chips are even more vulnerable. More bit flips are happening earlier. So we basically said, solving this perfectly is difficult. I'm going to show you actually some numbers. And also, if you look at that number, there are some new chips whose weakest cells fail after only 4,800 hammers. That's a very small number. Just to give you a perspective, you can hammer in an activation. Actually, this is double-sided, so it's really 9,600 activations. But in a 64 millisecond refresh interval, you can fit 1.4 million activations. We're talking about 4,800. Some real workloads may actually be causing this. In fact, there's a Microsoft paper at ISCA 2022, I believe, that showed that you can induce these hammers using coherence mechanisms, and some real workloads actually fail. There are some other stories, but I will leave that for later. Basically, we also showed that existing mitigation mechanisms are not effective at future technology nodes if the scaling keeps going like this. So imagine you get a bit flip after 100 activations to a row. That's very difficult to prevent. In fact, many benign workloads actually can do that. Okay, so I'm not going to bore you with a lot of details of this paper since we have a lot of other things to cover. But we tested a lot of DRAM chips. We built a lot of infrastructures to be able to test those DRAM chips. So this is an infrastructure-heavy thing. Let me give you some result over here. So if you look at these are different manufacturers, and you're going from old DDR4 chips to new DDR4 chips here. And this is the hammer count at which, this is hammer count on the x-axis and the bit flip rate that you see on the y-axis. So clearly, as you go from old technology to new technology, you get more bit flips at smaller hammer counts. Right? So basically, it's getting worse. And that's true for all manufacturers, as you can see. So how do the solutions scale? So we also studied that in simulation in our paper based on real data from real chips. So this is number of hammers required to induce the first RowHammer bit flip. Going from left to right, it reduces. And this is the performance impact of a solution. And these are real chips that we tested. So going from DDR3 old to LPDDR4 new, you're really marching from left to right. The hammer count to induce a bit flip is reducing significantly, as you can see. This is the increasing the refresh rate across the board. Terrible solution, as you can see, right? You have a huge performance impact. Higher is better over here. Ideally, you would like to have 100% performance, which is your solution doesn't affect the performance of the system. Para, which was our solution, gets worse as the hammer count goes below about 1,000, right? There are some ideal solutions that even they get worse over here. So basically, we said that we need to develop better solutions that can scale with the problem. Okay, we also studied a lot of RowHammer characteristics. I'll go through some of these relatively quickly. This was a paper that we published in 2021. We basically wanted to understand how temperature affects things, how aggressor row active time affects things. We're going to talk about that later on. And how the errors are distributed in the physical location in DRAM. And we essentially showed that some things we don't quite understand. So temperatures, for example, if you look at temperature versus retention time, you get a beautiful curve. As temperature increases, retention time reduces exponentially. So you can actually draw that curve and fix the issues with, in fact, many DRAM chips today have temperature compensated refresh. As the temperature increases, you increase the refresh rate. In RowHammer, there's no such thing. There are some cells that are vulnerable at a particular temperature interval. So each cell has a vulnerability window in terms of temperature. And we don't quite understand this, frankly. This is consistent with some of the lower level device studies, but this is not good in general. I'll leave it at that, because solutions are not easy in that sense. We saw that if the aggressor row is active for a longer time, you get more bit flips. I'm going to talk a lot about that later on. And in certain physical regions of the DRAM module that's under attack, you get a lot more bit flips. So you can take, for all of these observations, you can take the attacker perspective. If the attacker knows more, they can craft a better attack. They can cause more bit flips. If the defender knows more, they can craft a better defense. Right? So that's why we need to understand better. I'm going to skip this one because I'm going to talk more about this, but I'll talk about this a little bit. So about 10% of the DRAM cells have much higher vulnerability, double the vulnerability of, let's say, the remaining 90%. So if you can figure out which DRAM cells are more vulnerable and which DRAM cells are less vulnerable, you can have a better defense, for example, right? And we actually have a paper coming out at HPCA that studies this effect plus aging a lot more. It's not an easy solution because you need to keep track of which cells are vulnerable by how much, but maybe there could be mechanisms there. Okay, there's more over here. So we did more RowHammer analysis that I'm not going to talk about. For example, word line voltage. You activate the word line, you apply some voltage, but you have some lever over there. You can reduce the voltage or increase the voltage. Right? As you increase the voltage, you become more vulnerable. As you reduce the voltage, you become less vulnerable to RowHammer, but now your latency increases and your retention time starts having issues. So there's no easy answer, basically, after analysis of many, many DRAM chips and after building this infrastructure that can actually control the voltage at plus minus 1 millivolt granularity. So I empathize a lot with the manufacturers in this sense. They have a complex trade-off space. If they change something, it affects a lot of things in the system. So the solution is not that easy at the device level also. Okay, so as I said, HBM chips are vulnerable, and we have papers on this, so you can take a look at it. Now let's talk about solutions. Feel free to interrupt me with analysis also, because I'm going to switch back to analysis maybe a little bit more later on. Yes?
If only like something like 10% cell are more vulnerable to that, is that possible? Like for you to do a big issue in the operating system background, you do a periodically scan, like you just do the RowHammer attack on all the regions and just labeled the more easy to file region, those physical addresses, and you black them out. You just don't use them.
I see. Yeah, I see. Okay, that's an interesting solution. It's good to develop such solutions. As the RowHammer threshold reduces, like becomes very, very small, it becomes very difficult to get rid of those cells. You can make a more efficient solution, but the solution that you mentioned, I think, will have very high overhead.
Yes.
Yeah. But I think I like the idea because this is similar to what I'm going to go towards, which is more online profiling of memory. So we cannot manufacture perfect memories, and these memories will age. So over time, we should keep doing testing and understanding what's happening in the memory controller and adapt our solutions based on the vulnerability of the device. So I like that aspect of it. But we need to figure out how to do this at low overhead. And I don't think we know that yet. Yes, another.
So, like there is DRAM, right? Like we have flash, right?
Yeah.
So won't be accessing DRAM a lot because of cache.
Yeah, but you can bypass the caches very easily. And there are workloads that don't benefit from caching. So if you want to craft an attack, you can bypass everything. You can actually reverse engineer almost everything in DRAM and figure out what's happening and craft your attack. And we can do this very easily on an academic budget. Security researchers can do it. Imagine what people can do if they actually have a lot of money and they're motivated to do this. Yeah. And there are some benign workloads that also bypass the cache because they have terrible caching locality. Okay, so let me talk about a little bit more about what happened. While we were doing these device level studies, we also asked the question, DRAM manufacturers claim that their solutions work and their DRAM is secure. Is that true? We collaborated with security folks. This is where our FPGA infrastructure was very handy because we were able to reverse engineer a lot of what DRAM manufacturers actually did internally in DRAM. I'm amazed that they didn't think about other people doing this. If we can do this, I think anyone can do it. But basically, the idea is this. You have a solution internally. It's a poor RowHammer solution, right? If you don't want people to pass through that road, you don't build a gate like that, right? You can bypass the gate. Okay, I'm going to use this picture later on again. But basically, this trespass work. So what DRAM manufacturers did, there was this TRR, targeted row refresh, that's introduced into the DRAM standard, DDR4 standard, which basically said you do refreshes in targeted rows. That's it. Nothing really detailed. So it was a very broad thing that's introduced. So internally, DRAM manufacturers could implement in different ways. And we basically showed that these TRR-protected DRAM chips are vulnerable. To do this, we were able to bypass the internal mechanisms. So what are the internal mechanisms? That's what we discovered with reverse engineering. Internal mechanisms usually keep track of some number of rows. So they count, for example, how many the accesses that happen to 4 rows or 16 rows. And if you so they have internal tables in DRAM to do this. If you overflow these tables, then your counts are completely inaccurate, right? And that's essentially what we did. We introduced this many-sided RowHammer attack as opposed to hammering 2 rows. You hammer 20 rows, and then you bypass the tables, essentially. And internally, they cannot keep track of the activation counts accurately, and then you introduce Bitflips. So basically, you're back to square one. So to do this, we reverse engineer things, and we actually provide an automatic tool. And you can use this. Later works actually improve this. But basically, this is what the attack looks like. So normally, a double-sided attack looks like this. You have the red rows that are being hammered. This is a 3-sided attack. You have 3 rows that are being hammered. Here, you have a 4-sided attack. And this is different DRAM chips. This is the real results from real DRAM chips that are protected against RowHammer, remember. So on some of these, after hammering 5 rows, you get a lot of Bitflips. I mean, some of this is noisy because there's some internal management mechanism that they use for the tables that we didn't completely reverse engineer in the original paper, but we almost completely reverse engineered in the later paper, as I will show you. Okay, so these are the attacks. In this particular paper, we were able to show that all manufacturers are vulnerable, but not all of the chips that we tested were vulnerable because this was enough of a result for us. So for example, for some chips, the best pattern is 19-sided. You hammer 19 rows. For some of them, it's 3 rows. And then we actually took real mobile phones, and we were able to induce Bitflips in real mobile phones also, as you can see. 5 of them were enough for us. And we actually replicated the attacks that were proposed in the literature. The page table attack is, for example, Google's attack or variant of that. There are attacks on cryptographic keys, RSA attacks, and there are also other attacks. And we were able to actually do the full attack on chips that are advertised as protected for RowHammer. So it's fascinating, I think. So essentially, and these results were also scratching the surface because our tool was not exhaustive. We didn't perfectly reverse engineer. So we said there's a lot of room for uncovering even more vulnerable chips and phones. And the conclusion was RowHammer is still an open problem. And security by obscurity, like manufacturers did, was not a good solution. I still believe that both of them are true, actually. And the second one is even more true. I think manufacturers are going still the same route, although they're implementing better solutions, as we will see. Well, better, but more costly also. Okay, so these two works, especially the revisiting RowHammer work and the trespass work, cause a lot of churn in industry, and especially the hyperscalers like Microsoft, Google, etc., put a lot of pressure on JEDEC and said, we need to solve this problem. And they actually recreated the task group that was disbanded after manufacturers claimed that this was over. And then they actually put out these white papers that are kind of interesting, but very high level. You can take a look at that. So we uncovered TR almost completely after this. I'm going to go through this relatively quickly unless there are questions. But basically, you can reverse engineer almost everything. If you have this FPGA-based infrastructure, and if you know what's going on inside your DRAM, you can do a lot of interesting things. So this is where we used our knowledge about data retention times. So internally, DRAM chip is doing some sort of refresh to mitigate RowHammer, right? How do you figure out which rows are being refreshed and when they're refreshed? Now, if you know the retention time of the rows, you can basically turn off regular refresh for a while and say this row is going to lose its data, assuming it's not internally refreshed for some other reason. Right? So we did that, and we figured out that internally there's a RowHammer mechanism or RowHammer mitigation mechanism that refreshes these rows that would otherwise lose their data, because we know the properties of all of the rows because we tested all of them. Right? So this way you can actually figure out exactly when a DRAM chip issues a refresh, for what rows, under what conditions. And we were able to actually reverse engineer. At some point we said, okay, stop. we don't want to do reverse engineer more. But you can see that different manufacturers, I think this is Samsung, uses counter-based mechanisms. They keep track of 16 rows per bank, and they do refreshes RowHammer refreshes every 9 regular refreshes, etc. Some other, this is I think Hynix, they use sampling-based mechanisms, so their capacity is only 1, etc. So basically you can figure out everything. And once you figure out everything, you can craft much better attacks. And that's what we essentially did. And going back to the ECC question, you could bypass all kinds of ECC, even if you were able to build some of this. So basically we induced a lot of errors. And this number is going up, basically. Okay, so you can reverse engineer everything. While we were doing this, there are also other folks, like Microsoft and Google. I'll mention Google's work over here, because this is actually really interesting. These folks discovered an effect that they called half-double. So basically, this is a regular RowHammer, right? You have a single aggressor row and you have victim rows. Now, they hammered this aggressor row many, many times, A, and they hammered this aggressor row B very little. Like, think about this as 10,000 times and 100 times over here, and they were able to induce Bitflips in victim rows. Now, the significance of this is, if you're hammering this aggressor row many times, and if you have an internal refresh mechanism, that would refresh aggressor row B. And now your internal refresh mechanism that's trying to protect Bitflips in aggressor row B can cause Bitflips in victim row C. So your solution can become an attack. And I think this is very fascinating. So now your solutions need to be carefully crafted. And these numbers actually, all of these become worse as the number of hammers reduces over time. Okay, they published a Unix security paper on this topic. You can read it. Maybe they have the source code available. I'm not sure. Okay, so people kept developing solutions. I'll mention this one relatively quickly because I think we need to think out of the box a little bit. This was more of an out of the box solution at the time. Essentially, we wanted to solve the problem without relying on DRAM. And I think it's good to try to do that also. So we wanted to do it at the memory controller. And the idea here is you have area efficient Bloom filters. And these Bloom filters keep track of which rows are activated by how much, approximately. And if you figure out a row is activated a lot, with some false positives, of course, the memory controller selectively throttles accesses to that row. And you can build a solution that's completely secure, such that Bitflips do not occur. And you can also optionally inform the system software about the attack, because now you have counters, etc. So we showed that this is actually implementable completely in the memory controller without relying on DRAM. And this is another intelligent controller. Now, unfortunately, this doesn't scale to like hammer counts of 100 also. So we need to be even more innovative and creative so that we can actually solve this problem better. And this has overhead. It has less overhead than some other solutions, but still has overhead. Okay, so I think we need to have even more intelligent controllers for this sort of problem and more. So we're back to this picture, basically. Now, let me tell you what industry finally did. Well, I don't think it's final yet, but finally for us, let's say, after almost 10 years, they wrote a paper. SK Hynix wrote a paper. It's very hard to read because it's only 2 pages and they don't reveal a lot of stuff. But the good thing is they mentioned RowHammer. Industry didn't want to know. Industry meaning DRAM manufacturers. Microsoft and Google were happy about talking about RowHammer because they wanted the problem fixed. DRAM manufacturers did not talk about it for a long time, but finally they wrote a paper at ISCA, partially because of all of the pressures that have been coming. And they basically said they have some solutions to RowHammer. Essentially, the idea is putting intelligent controls in the DRAM chip. So if you actually went to industry like 10 years ago, which we did, and told you, oh, you should really put intelligence in your DRAM chips, they would kick you out of the room. I mean, they're nice. They don't do that exactly, but that's the gist of it, basically. Now, 10 years later, they're putting intelligent control. So what they did, basically, one of the solutions, at least here, which I believe is not completely good, but it's at least a step in the right direction. People are thinking intelligent controls, etc., is they associated counters with each DRAM row. So it's an expensive solution. Each DRAM row has a counter associated with it. And internally, they keep track of activations, and based on some magic number, they refresh some adjacent rows. They don't talk about it in detail. So they claim that they reduced the RowHammer vulnerability. So they're smart. They don't claim that they fixed RowHammer completely, but they reduced the RowHammer vulnerability. But there's no analysis, etc. So it remains to be seen. I believe industry is taking a direction somewhat like this, but we'll see. So Samsung, of course, after seeing that SK Hynix has a paper that's coming up at ISCA, they had to write their own paper. Very hard to read paper. I don't think this is a good solution also, by the way. This is not their final solution in the end, but you can take a look at it. So actually, Microsoft and Google have also been proposing solutions. This is a solution that Microsoft proposed at DRAMSec in 2021. It's essentially counters per each row, but it also gives some time to the DRAM chip. So if the DRAM chip cannot handle a lot of activations, it basically says stop to the memory control. I'm going to talk about that a little bit more, but I think the general idea is a good idea. So we will see how things play out. At least the industry is much more open about this problem at this point. Are we doing okay on time? Okay, I'm going to talk about RowPress. I don't want to spend a lot of time and then talk about some future. But feel free to ask questions. So the question is, are we now RowHammer free in 2023 and beyond? Now we're in 2024. I don't believe so. And we need a lot of other issues. We have a lot of other issues. So we introduced this RowPress issue at ISCA in 2023. Essentially, this is another read disturb phenomenon that caused Bitflips in real DRAM chips. It's different from RowHammer. I'm going to show that. You can induce these Bitflips with a user-level program on a system that's protected against RowHammer. And we provide some solutions, although solutions come always at a performance cost. So basically, what is RowPress? If you keep a DRAM row active for a long time, you activate it, and you open it, it's in the row buffer, and you keep it like that for a long time, this causes Bitflips in adjacent rows, which is fascinating. These Bitflips don't require many row activations. We tested this many chips. Only one activation is enough in some cases. So you activate one row, you wait for 30 milliseconds, you get Bitflips in adjacent rows. I think this is fascinating. Clearly, that's bad. This is violating the DRAM timing parameters, but you would not expect Bitflips like this with RowHammer, right? Because it's only one activation. So let's take a look quickly. So basically, we asked the question, what if there was a read disturb phenomenon that doesn't rely on high activation count? Again, we're back to this picture. All of the solutions detect high activation count and refresh or throttle. Can we actually bypass these solutions? So this is what RowHammer looks like. You activate a row as frequently as possible, as much as it's allowed by the DRAM standard. So you have 47K activations in this particular example to induce Bitflips if you activate as frequently as possible. RowPress said, let's not activate it as frequently as possible. Let's keep the row open for 7.8 microseconds in this particular case, which is legal in DRAM. You need only 5,000 activations. So if your solution is configured to trigger after 50,000 activations, well, it shouldn't be 50,000. After 40,000 activations, let's say, you'll get Bitflips. And that's what we essentially showed. So we did these studies with DRAM vendor. Again, we covered all of the manufacturers. Now, we don't hide their names anymore, as you can see. There's no reason, I think. Yeah. It's actually interesting. Security community never hide names, right? You have a vulnerability in Intel chip, AMD chip. But DRAM is a very different field, but we need to be more open. Yeah. Okay, so basically RowPress significantly amplifies DRAM's vulnerability to read disturbance, and it has a different underlying mechanism. So let me give you some examples. So this is RowHammer. These are 3 different manufacturers again. You activate as frequently as possible, and this is activation count that you need to induce Bitflips on this particular set of chips from this manufacturer. That reduces significantly if you keep the row open 7.8 microseconds. And that is even more significantly if you keep the row open 70.2 microseconds, which is the maximum allowed by the DDR4 standard today. So these 2 are legal. So you basically reduce the number of activations to induce a bit flip by 1 to 2 orders of magnitude. So attacker's job is easier now. And if you actually violate, only one activation can cause bit flips in all of the chips that we tested, which is also fascinating. Okay. So this is different from RowHammer because as temperature increases, this effect gets worse. RowHammer doesn't have this sort of relationship. And there also, it affects different set of cells. It's a completely different set of cells, actually. And I already said this, but there are also access pattern effects that are different from RowHammer. So we showed that on a real system, you can build a proof of concept program that induces these bit flips. Essentially, how do you keep a row open on a real system? Clearly, we don't have control over the memory controller, but we have control over the program. The program can keep accessing consecutive cache lines in the same row, assuming that consecutive cache lines map to consecutive rows, the same row, which is the case in many systems, and hopes that the memory controller keeps the row open. And that's true in many memory controllers today. Intel has this adaptive row management policy, which keeps the row open for some time. And we were able to induce bit flips if we keep the row open long enough, as you can see. And actually, in Appendix G of the extended version of this paper, we improved this program, and you can use even more bit flips than this. Okay, so how do you mitigate this? Basically, the key idea is you need to limit the row open time by some amount. But of course, if you limit the row open time, you lose locality, right? So we basically said you need to limit the row open time, otherwise the problem gets out of control. But you exploit some locality at least. Now, once you limit the row open time, you adapt the RowHammer mitigation to take effect earlier, meaning at a lower activation count that corresponds to a row being open for that row open time. Essentially, that's the idea. So it requires testing and understanding, etc. But this was our solution. And we showed that you get full security with some performance overhead. So performance overhead is the unfortunate aspect of all of these, unfortunately. Okay, there's a lot more. If you want to build on this work, you can. It's all fully artifact evaluated, and we'd be happy to support you. It was replicated by people in industry, by the way. Yes? Okay, sure. Okay, so that's the paper. I believe there's more to come. This is not the end of it. So I already mentioned these two major directions. I think we should be working on these. And if you're interested in the survey, so we've been writing a lot of other papers arguing that we should really have a different way of looking at things in industry. So we should have more transparency in memory. So if the memory vendors actually share a little bit more, at the system level, you can do a lot more. So for example, even if the memory vendors provide the row layout, right? Which rows are adjacent to each other, that could help build solutions. If they provide actually vulnerability of the rows, that's even better. Of course, we have some ways to go to change the mindset, let's say. So I'll mention this a little bit, but I think maybe we should also be thinking about a different interface to the problem, because memory manufacturers actually know a lot, but they cannot do a lot inside the DRAM chips. So they don't have complete control. So we've come to a situation where memory controller is controlled by processor companies and DRAM is manufactured. DRAM has no intelligence, almost. And it has very little breathing room, because memory controller is very tight in its control, right? It has timing constraints, and DRAM needs to obey those timing constraints. If it wants to say to the memory controller, oh, stop, I want to have some breathing room so that I can fix some of the issues that I have internally. Basically, the idea of self-managing DRAM is to give the breathing room to the DRAM. It's a very simple idea. The DRAM can reject some row activation commands, saying that, oh, I'm doing something else. Don't bother me for a while. So that's the idea. This requires very little changes. And what does this enable is interesting, actually. It clearly enables some RowHammer protection, because DRAM can actually protect against RowHammer, especially when combined with a solution like per row activation counters or some other solution. This could also help manage refresh a lot better. So a lot of the work that we've done on refresh over more than a decade, I believe it can be managed much better if you have an interface like this. Because DRAM manufacturers can figure out a lot about their DRAM chips and put a solution. They just don't have time to actually do some internal management inside the DRAM. And then there's memory scrubbing that we talk about in the paper. So you can take a look at the paper. And that was part of my PhD student Hassan's thesis. So there are more intelligent controllers coming up that I'm not going to bore you with. You can take a look. This is going to appear at HPCA, this at Unix Security. But there's more also other people are doing. So there are RowHammer sessions and conferences, as you can see. This may not be a complete picture. So if I missed your paper, sorry. So there's more analysis also coming up. Okay, Now let me take a step back, talk about future memory. Do we have time? Or I see here.
Yes, we're fine.
Okay, if you don't want me to talk, ask questions. Okay, so what does the future bring? I think future is bleak. Meaning, DRAM is actually becoming more vulnerable, as you can see. I think there are other effects that we have not discovered. I believe actually retention errors may be slipping into the field. It's very hard to figure that out or exploit at this point. But who knows? There are a lot of creative people in the world. Now, somebody mentioned other memories. Like flash memory is clearly very vulnerable, but flash memory I'm not as concerned about as a security problem because you have an intelligent memory controller and people actually are very good at building those memory controllers. But emerging technologies. What about emerging technologies? Is there a technology that can replace DRAM? If you asked me that question maybe 15 years ago, I would say maybe. Right now, if you ask me, I think it's very difficult. Even though we have all these scaling issues with DRAM, it's not easy to find another technology. People are looking at, for example, ferroelectric DRAM. They call it MV-DRAM, for example. I think there may be something there, but it's still not there yet. We still need at least 5, maybe even 10, maybe even more years. So at that point, DRAM scaling may be much worse, of course, right? So I think we need to investigate all these technologies, of course. Maybe having hybrid memories will help. I think no question about that. But I don't think there's any technology that's immune to this sort of effects. So how do we build robust memory systems in the presence of all of this? I don't have the solution, of course, but I think I have some principled methodology at least. I believe we need to understand more. We don't even understand some of these effects, right? One of the reasons why RowHammer actually slipped into the field was there was not enough understanding developed. I think we're in a better place right now, but maybe we are not still completely understanding. We need to develop methods for vulnerability modeling and discovery, and we really need to test real devices more and more. Do it online also in the field. Understand aging, for example. And then we need to architect better. Right now, I think the partitioning of duties between memory controller and memory is really not good. I think we need to rethink that interface over time. We cannot give up performance and efficiency, and we need to have better memory controllers, whether they're on the processor chip or memory. They need to be more patchable. So if you discover an issue like this in the field, let's patch it, right? And maybe discover these issues in the field, right? That's design and test, basically. Do more online testing, principled design, such that over time you discover these issues before others discover it for you. Right? So I think there's a lot more work to be done. Online testing is very interesting from the CPU domain also, I believe, but memory needs to have more of this as well. So that's why we've been building a lot of infrastructure, and we'd be happy to help more. Let me go back to bridges. I'm almost at the end. I'm going to give you some bridges and a historical perspective. So these are bridges. So bridges are something that human beings have been building for thousands of years. And we still did not get it right. This is Seoul, this is Genoa, this is Neapolis. This is a place close to my heart because I went over this Forbes Avenue Bridge for a long time at Carnegie Mellon, close to Carnegie Mellon. And you could argue why this sort of things happen. But clearly, we're not able to be completely robust, right? And I think computing is even worse than bridges, right? We take a lot more care in bridges, etc. In computing, we take a lot less care, if you will. But we need to take a lot more care, in my opinion. So we need to rethink how we design robust systems. And I believe intelligent memory is going to be part of the solution. So, but I think there's a general problem, which is not just related to memory, but how do we build fundamentally robust systems? And that really is a systems problem in the end. I think memory is a systems problem. Hopefully I've convinced you. Now let me give you some final thoughts. So under the sun, there's nothing new, actually. These read disturbances have been known for a long time, even to the security community. So these folks, this is actually quite innovative paper from Princeton. It was published in 2003, IEEE Security and Privacy. What these folks did was, they introduced memory errors. And they showed that if you have memory errors, you can take over the Java virtual machine. You can escape the sandbox. How did they introduce memory loads? They basically had a lamp. And once you have a lamp and heat up your memory, you get a lot of memory errors. Clearly, this is an attack model that's not very, let's say, viable in many circumstances. But it's very creative.